To help review for DCP number 3, we have made a review where there's about 2 of each type of question. So I will go over one of the 2 of each type of questions with you and leave the other one for you to do on your own. We'll go ahead and get started. The first one, for number 1 and number 2, the directions ask us to graph, or that the graph of the exponential function is shown. We need to label the domain, range, y-intercept, and initial value, draw in the asymptote, and then identify the equation of the asymptote. We're going to start with the easiest part, which is drawing in the asymptote. Remember that the asymptote is a vocabulary word that's essentially the same for every single one of the exponential functions we deal with. It's the line that the graph will come very close to but never touch. For exponential functions, it's a horizontal asymptote that appears at the x-axis and basically splits it into a top part and a bottom part. That is the asymptote for this graph. Now, because we're humans, we can't really draw that well. It looks like mine is touching, but if we were to zoom in on a graph, it would never touch those 2 lines. The dotted line I drew in, your x-axis, and your curve would never touch. Okay. Since it is our x-axis, the asymptote's equation is y equals 0. It's the flat line at the height of 0. Hoi is a horizontal line at the number 0, so that makes sense that it's our x-axis. If we look at the domain of an exponential function, domain is the x values, so we're looking along the x-axis for where the graph stops, begins, ends, all of that thing. So if we look on the side, we notice that this curve is going to keep going and going and going and going and going and going and going all the way to negative infinity. And if we look this direction, it goes up, but it's going to keep going and going and going and going and going and going and going all the way to positive infinity along the x-axis. It's never going to stop. When it never stops from one direction to the other, we would answer all real numbers. The range is asking about the y values. So we're looking along the y-axis. If I look from the bottom to the top of the y-axis, we already talked about the fact that the asymptote is a line it's never going to cross. So this graph is never going to appear down here. The curve should never show up down there. It can't cross this line. So that means the lowest spot it's going to be is here at 0, and it's going to keep going up and up and up all the way to positive infinity. So we would say that the whole graph appears above the line 0. Greater than is the above symbol. If it was below, we use less than, but since this whole curve is above my asymptote, it's a greater than. The y-intercept's easy. We can always identify it on the graph. That's the y-intercept because it's where it crosses the y-axis. And for us, the y-intercept is 0, 1. In between 0 and 2 is 1. Therefore, my initial value of this function is 1. Whatever the y-intercept is, your initial value is as well. It's a great way to eliminate answer choices. For number 3 and 4, your first instinct when you're asked to write an equation given a table is that if you see a table, you can do stat, edit, enter. You can solve this one by hand just by looking at it, but if you would like for me to go over how to stat, edit, enter, we'll do that right now. So when I grab my calculator, I'd go to stat, I'd enter the table 0, 1, 2, 3, and 0.025, 0.2, 1.6, and 12.8. We'd go to stat and over to calculate. Now, we've used 4, and we've used 0. Since this one is telling me that it's an exponential function, / I notice the numbers are going up really fast, we would know that this is a 0 and exponential regression. On this store regression equation, we press alpha trace, enter to put a y1 right there. It's a shortcut for our calculator. And we calculate, and it would tell me, following this pattern that it tells me right there, that my function is y equals 0.025 times 8 raised to the x power, which makes sense because my initial value at 0 is 0.025, and every time I'm multiplying by 8 times 8 times 8 times 8. So this function makes sense, but thank you, calculator, for telling us as well. For number 5 and 6, it's asking you to identify the initial value and the rate Then write an equation that represents each situation. When we're given a rate, we're given it usually in percentages, and to write an equation, we need it as a decimal. So we need to make sure we're using the decimal version of that percent. Knowing additionally that it's a percentage question, we know that this is going to either be growth or decay. Growth and decay followed this formula, where you have an initial value, a 1 plus for growth minus for decay, and then that rate as a decimal, in parentheses, raised to the t power. So for example, if we look at 5 and it says a school population of 1,200 decreases by 6% each year. So that means the school population was initially 1,200, that the rate is 6%, but I can go ahead and change that with the Dr. Pepper rule to 0.06 so that I use it correctly. And since I'm decreasing, I'm going to use a minus sign in my formula. So my equation following this exact pattern, using my initial value and my rate, would be y equals 1,200, 1 minus 0.06 raised to the t power. That is an okay answer, but your answer choices may also look like the simplified version, where you actually do 1 minus 0.06 in your brain or in your calculator to get 0.94 raised to the t power. Those are literally the same question. One is expanded so you can see the subtraction sign and the rate. One is condensed so you just have a factor, like a regular exponential function. On number 7 and 8, it's asking us to identify the y-intercept, the initial value, and then write another equation. Since this is given to you with coordinates, you could totally stat edit this. It's like you have a table of x's and y values, but we're going to do this one in our brain because we're fully capable of that. We know immediately that the y-intercept is where the curve crosses the y-axis, and right here we have the point 0, 3 as my y-intercept, which means that my bacterial population on day 0 when I started this experiment was 3. I had 3 little bitty bacterias. To write the equation, all we need is to fill in the regular exponential function where we have an initial value and a factor, or how it's changing each time. So this is initial value, this is how it's changing each time. Well, we know immediately that my initial value is 3. We already talked about that. All we need to know is how it's changing from one day to the next in this experiment. So the first day, or when I started my experiment, I had 3 bacteria. The next day I had 9, then 27, then 81, then 243, then 729. So if we look at this pattern of numbers, what's happening each time? Well, it's multiplying by 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3, 81, and on and on. So this factor, or what's happening each time, is that I'm multiplying by 3. If you don't believe me, you can always check this sort of question in your calculator. A 30-second check to guarantee I have the correct answer is a great testing strategy, especially for hard tests like the DCPs. We put in exactly the coordinates that we're given on the graph, and it creates a table for us. Graphs and tables represent the same information, just different visuals. Since this is exponential, it's a curve, we would choose what number? 0. Making sure it says exponential regression at the top. We store the regression equation in y1 and calculate. And it tells me that I have an initial value of 3 and it's multiplying by 3 both times. Woohoo! 30-second check. We know we got that one right. Number 9 says, the table shows the number Y views of an online video received after being online for X days. So this is about going viral. A video started and the first day it was posted, it had 12 views. And then a bunch of people shared it, so after 1 day it had 68. And then after 2 days, and 3 days, and 4 days, and 5 days, wow. So we're going to use a graphing calculator to write an exponential function that fits the data, which makes sense because we see a table and it's asking us to write a function or write an equation. Helpful data is always coming from getting equations. Okay, so let's do this again. We're going to stat edit. Clear out what we have. I'm clearing it, by the way, by going up to the L, pressing clear, not delete, clear, and then enter, and it gets rid of everything. 0, 1, 2, 3, 4, 5. 12, 68, 613, 3996, 27, 810, 205, 017. We calculate. Now this is an exponential function. It's going to tell you what kind of function it is when we do multiple functions at a time, so make sure you're looking for that keyword. We choose option 0. Make sure it says exponential at the top, and we alpha trace inner. This would tell me that my video is growing at a function that can be represented by 11.13 times 7.11, rounding to the nearest hundredth, to the t power. That is describing the growth of this video, or how this video is going viral. Part B says to predict the number of views the video receives after being online for 7 days. Days is my x value, which means it would go in my exponent. So I could type in my calculator 11.13 times 7.11 to the 7 power. But since we did the extra step of putting the y1 in my calculator, it has automatically loaded all of this data into your graph and table. I want to look at the table, so I press second graph and it takes me to my table. These are all the data points gathered from your function here. So we want to look at 7 days. Here's day 7. This is how many views your video would have after a week. If this was a really good and viral video, you'd have 10,212,588 views. Ten is very similar, so I'm leaving that one for you to do. 11 and 12 are similar, so I'll do 11, you've got 12. 11 says a young channel catfish weighs about 0.1 pound. That looks important. During the next 8 weeks, its weight will increase by about 23% each week. Write an exponential function that represents the weight of the catfish after t weeks. If we're given a percentage and asked to write a function, we know that with percents we have to use the growth or decay version of our exponential function, where we include the rate, not a factor. Well, the channel catfish originally started at 0.1 pounds, so I know its initial value is 0.1, and then it increases, that's a plus sign, by 23%. Well, 23% is 0.23, and I know I have to make it a decimal to put it in my formula. This is an okay answer, or you can write the simplified version. Some of your answer choices may look like the simplified version where we actually add or subtract these numbers. So this would be an adding problem. 1 plus 0.23 is 1.23. Those are the same equation. This one tells me a plus sign and the rate. This one tells me the factor. Rate, factor. On to the second part, which is sequences. If we remember, sequences are just lists of numbers with a pattern. List of numbers with a pattern. All we have to do is figure out what pattern we're using and continue that pattern to make our list of numbers. Number 13 tells us in the complicated format that sequences uses, a sub n equals a sub n minus 1 plus 1, given a sub 1 equals 18. Confusing notation, simple information. A sub 1 tells me that this is the starting number. Whatever is a sub 1 is what you're going to start with. This part right here tells you the pattern. Now I legitimately see a plus 1 here. That means we're going to start with 18 and we're going to add 1 to make my list of numbers. So to identify the first 4 terms in this sequence, we start with 18, add 1, add 1. Add 1. Look, there's 4 terms. I did it. Sequences keep going, so it's going to have this funky notation at the end if you're writing a full sequence. Okay, those are the first 4 numbers. I started at 18, and I added 1 each time. 14 is for you. 15 says a sub n equals 3, a sub n minus 1, given a sub 1 equals 4. Confusing notation, simple information. Again, a sub 1 tells you your first or your starting number. I know this one starts with 4. So there are answer choices that don't start with 4, don't pick those. Then I have to look here. I don't see an add or subtract sign. I see 2 things smushed together. When things are smushed together, we are multiplying. So this is telling me that I'm going to start with 4, and I'm going to multiply by 3 each time. 4 times 3, 12. 12 times 3, 36. 36 times 3, 108. It started with 4 and multiplied by 3 each time. For 17 and 18, it says to write a rule or a formula. It doesn't tell us what kind of rule or formula, and we know we learned about 2 different types of rules. We learned about explicit and recursive. We're going to write the explicit rule, so if you need help on recursive, that might be a question you can ask your teacher. But for the explicit rule, for a sequence, we really can pretend like this is a linear or an exponential equation, and in which case we see data points that kind of make a table, and we can stat edit. So we'd grab our calculator, we'd go to stat, and we'd go to edit. We'd type in the points that we see. There's a first step, a second step, a third step, a fourth step. Those are the numbers in my sequence. We started with 4, we had 8, we had 12, we had 16. Now, if you look at the difference between this data and this data, this is going up, this one's going down, but they're both going in a straight line. When you have a straight line, that's a linear. That's number 4. So when I go to stat calculate, instead of picking 0 for curves or exponentials, I'm going to choose the line, the linear regression. We store the regression equation. Oop, I clicked the wrong button. We're going to store it in alpha trace inner, y1, and calculate. It's going to tell me that my formula is 4x plus 0, which makes sense since this is a linear equation. If I were to connect all these points together and let it continue that way, you'd notice it starts at 0 and it's adding 4 each time. We get to my favorite unit. I love polynomials. So polynomial arithmetic is super fun. It's just some straight up math. For these questions over here, I'm going to do this column. You'll have this column for yourself. It says to perform the operation and write a simplified equivalent expression. This word equivalent is super important. So is the word simplified. Okay, we're just trying to simplify these down, doing whatever operation it says to do in between them, and making sure that the beginning and the end are equivalent or the same, which will help us check our work. If they're the same, then when you graph both the beginning and the end, they should be the same. When you look at the table for the beginning and the end, they should be the same if they're equivalent. Now, when I taught polynomials to my class, I used the box method for everything. If you didn't use the box, you might need to go check your own notes for how to do it, or learn the box method like with me. For division, which is what number 19 is telling us to do, we would set up a funky box. This is a 2x2 box with a bunch of pieces everywhere. We might have a remainder, and we put the first piece of the dividend in the first box, the second piece of the dividend on the diagonal, and the third piece of the dividend on the center. Your divisor, or the smaller piece, goes along the side. The steps are just like long division, so if you learn long division, the steps will look familiar. You divide, multiply, subtract, and repeat. There's no bring down step for this, but repeat. Okay, we divide. X squared divided by x is a single x. Then we multiply. 1 times x is x. We subtract on the diagonal. 3 minus 1 equals 2x. 3x minus 1x is 2x. So I subtracted, then I repeat. 2x divided by x, okay, 2x divided by x is 2. 2 times 1, because we're multiplying, is 2. We subtract along my diagonal. 2 minus 2 equals nothing. Nothing to repeat because I have no more boxes, so I'm done. When we're writing our final answer, it is always the quotient from the top plus your remainder divided by your divisor, which is the small piece. Since this remainder is 0, I don't need this part. It's extra information. If there's nothing, it's nothing. So really, I would answer this one as just x plus 2. But if you get a remainder, you'd make sure you write it as remainder divided by divisor. 21 has no symbol in between these polynomials. And since they're smushed together, we know they're multiplied. When we're multiplying, we do still set up a box, but we don't put things inside the box. These start on the outside. It's like the Punnett square question. Since this is a binomial, 1, 2, 1, 2. This is a 2 by 2 box. You line up your individual pieces of what are called your factors along the outside and multiply inside like a Punnett square. 3 times 4 is 12. X times x is x squared. -1 times 4 is -4x. 3x times 9 is 27x. And -1 times 9 is -9. All right, so this one we add on our diagonal. We come this way to add. 27 plus -4 is 23x. So my final answer for multiplication questions, since it should be getting bigger, multiplying gets bigger, is the first number, the outside number, and the last number. So 12x squared plus 23x minus 9. '23 is super easy. Look, it's asking us to add these. When we're adding, all we have to do is combine our like terms. So we look for things that are like. If you remember, like terms mean they have to have the same variable and the same exponent. Same variable, same exponent. If we look for 3x squared, I'm looking for other things that have x squared in the entire polynomial question here. Here's another x squared. Add those together. 3 plus 5 is 8x squared. You don't change anything about the power here. When we're adding, you only change the coefficients. That's what combining like terms is. We've got an x. Oh, look, here's another x. 4 minus 6 is -2x. Don't change anything about the variable or the power. Then I have my constants. -7 plus 2 is a -5. And voila, I'm done. Simple as that. 25 is a subtracting question, which is almost just like adding, except we have to distribute a -1 from in front of that second parentheses before we start combining our like terms. So we change the entire second polynomial. The first one stays the same. I'm just going to rewrite it. Then I change the sign of everything inside here. So since this was positive 5x squared, it's -5x squared. This is positive 6x. This is now -2. That's what distributing a -1 does. If you don't believe me, check your calculator. Then we just have a simplifying question. Simplifying is just asking us to combine our like terms together. So same rules as addition. They have to have the same variable, same exponent. Don't change the variable or exponent, just change the numbers. 3 minus 5 is -2. 4 plus 6 is 10. -7 minus 2 is -9. Done. Easy peasy. Then we get to factoring. Factoring is super fun. It's like a giant puzzle. When we're factoring, we're trying to write it to where it's in factored form. Factored form. We start off with a long polynomial and we're trying to write it in factored form. It's like backwards multiplication. The first thing you always want to check for to make your life easier is a GCF. If you have an overall GCF between the 2 or 3 terms that you're using, your problem gets smaller and your numbers get easier. If we look at 27, we always asked, is there a GCF? Well, yeah, both of 2 and 72 are even, so I know that they're divisible by 2. So if I put that 2 in the front, just let them hang out in the front there for a little bit, we'd have x squared minus 36. You could use the long way we factored or realize that this is a difference of 2 squared. We're subtracting two things that are both perfect squares. Remember, 36 is actually 6 squared. So my dots pattern, which is on your formula chart, tells me immediately that if I have the difference of two things that are both squares, this automatically factors to x minus 6, first minus second, first plus second. Gotta let your GCF of 2 trickle down and be in the front, and immediately I'm done. Factoring is a giant puzzle. Number 30, I'm going to factor using the box method. If you learned a different way to factor, which is swing and divide, grouping, any other way you Googled about and found, please go ahead and use that on number 30. I'm not going to be offended that you don't use the box. I think the box is the most straightforward way to not make any mistakes. When we're doing our box, we know we want to factor. We want to write it in factored form. So we set up our box. We checked for a GCF. There's nothing common between 2, -7, and 5. We would put 2x squared in the top box and 5 in the last box. First term, first box, last term, last box. I set up my x puzzle so that a times c is in the top, which is 2 times 5, and b is in the bottom, b for bottom. I solved my x puzzle by figuring out numbers that simultaneously multiply to 10 and add to -7. You could make your list for 10 if you need it. The list for 10, only 10, don't make a list for 7, is 1 times 10, 2 times 5. Therefore, the only way to make -7 out of this would be -2 and -5. We write those into our box with an x after them. Since they came out of the x puzzle, they get an x in the box. All you're doing now is identifying GCF. You don't have to divide GCF, you're just identifying what they have in common. Numbers first, 2 and -5. Only have a 1 in common. X squared and x, the x is smaller. -2 and 5 only have a 1 in common. 2 and 2 have a 2 in common. X squared and x, smaller is x. 5 and 5 have a 5 in common. They have no number in common. Now I double check. I need to make sure that the number I wrote down outside the rows and the second row and the second column are the same sign as that box. So this needs to be -5 because this is negative. This one would have to be -1 since this is negative. If this was a positive box, this would be a positive number, but it's negative, so I use negative. Automatically, I know now that my factored form is x minus 1 and 2x minus 5. These are the numbers I got from the side and the top. We've gone and done backwards multiplication. When we multiplied on the last page, we started with factors and we made a trinomial. This time we started with a trinomial and we wrote the factors. Last question you're doing with me is number 35. When we are trying to write in factored form and find the solutions, we have two parts. We need to make sure first that it is equal to 0. This is not equal to 0. So when I pick this up and move it to the other side, it would change to the opposite sign and now be equal to 0. Check. Factored form is just what we did. Check for a GCF. 3, 11, and 6. Nothing in common, so I set up my box. We have 3x squared. First term, first box. Last term, last box. A times c in the top. B in the bottom. B for bottom. If you need a list for the top number, you make the list, or else you solve this part in your head. The numbers that multiply to 18 and simultaneously add to 11 are 2 and 9. 2 and 9 become part of my box. We've expanded the middle term, and we identify GCFs. Between 3 and 9, they have a 3 in common, and the smaller exponent is x. 2 and 6 are both even, so they have a 2 in common. 3 and 2, they have a 1 in common, and the smaller of the variables is x. 9 and 6, those are both divisible by 3. That's the biggest thing they have in common. Now I double check to make sure my signs are correct. This box is positive, so this factor has to be positive. This box is positive, so this factor has to be positive. So the factored form of this polynomial, answering half of this question, is 3x plus 2 and a single x plus 3. If it just asked me to write it in factored form, I'd be done, but it also asks me for the solutions. When I'm doing solutions, I want to set each individual piece or factor equal to 0. You take a shortcut or you do the math. The math to solve for x tells me to subtract 2 from both sides and then divide by 3 to isolate the x. My first solution would be x equals -2/3. take the shortcut or do the math. The math tells me to isolate x or get x by itself. I got to subtract 3 from both sides. There's my second solution.